Welcome to the Eberly Design webinar on NEMA Flashing Yellow Arrow Standard. My name is Scott Evans. I'm the Chief Technology Officer for Eberly Design. And this webinar is going to cover some basics of flashing yellow operation with respect to the MMU, the Malfunction Management Unit. And we are going to start off with a little background material on flashing yellow arrow, get into the need for it and the complexities of programming both the controller and the MMU, and then we'll see some examples of how the NEMA standard has defined the operation with respect to the MMU, and finally how we program the EDI MMU2-16LE smart monitor to configure it for flashing yellow arrow. So one of the premises of this webinar is that you already understand the basic signal operation of flashing yellow arrow. It's basically a replacement, if you will, for the conventional 5-section doghouse style of protected permissive left turn movements. So the need for flashing yellow arrow comes from several different directions. It was originally proposed back in the early 2000s. FHWA first issued interim approval for testing of flashing yellow arrow back in 2006. Prior to that, and we'll see in a minute when we get into the standards, NCHRP study kind of provided the research background for how flashing yellow should operate. We'll get into a little of those details further on. Basically, the flashing yellow arrow scheme is a 4-section signal head. The benefits are kind of summarized. It allows the protected and permissive left turn movements based on whatever the controller decides to sequence it at. It may be due to demand, it may be due to time of day. We can switch from protected, permitted left turns, lead lag, and with the exception of emergency preemption, we do all that without generating the yellow trap. So the yellow trap has been kind of a hang-up on protected permissive left turns, and we have several different examples over the years of schemes, louvers, and so forth to try and prevent it. It's an extremely flexible tool for the traffic engineer. We found that while it's a surprise to many drivers as we deploy it, once they see it and experience it, and with some minimal level of signage, it appears to have good driver understanding. So this is a great tool for the traffic engineer. Several studies have been done that have shown both a decrease in accident rate and an increase in vehicle throughput when an arterial is converted from basic protected permissive to flashing yellow arrow movements. All right, so the NCHRP 354 report was generated back in 2003. If you want to understand the psychological, the motorist impact, different things like that, the operation, this is the go-to story for a lot of the decisions that were made. Again, it was first published in 2003, and Federal Highway gave certain agencies permission to start testing it. At that point, Eberly Design got involved. If we're going to be testing new signal movements, we should have a conflict monitor that can detect when things go wrong. So we came out with a kind of a preliminary test unit back in 2005. So the point here is this has been going on for quite a few years. It may be new to you, it may be new to your agency, but there's a significant amount of experience behind both the MUTCD standard and the NEMA resulting NEMA standard. So After the test phase, MUTCD release in 2009 was published that basically defined the signaling conditions for flashing yellow arrow. What do the signal heads look like? How are they arranged? What is the sequence of signals? Things like that. So that kind of opened the door for, now that we know how flashing yellow arrow is to look to the motorist and operate at the intersection, NEMA got together and started work on adding to the NEMA equipment standard some detail on how controllers were to implement this, and more importantly how the MMUs would implement and monitor flashing yellow arrow. I'll mention that during the time from 2003 through 2012-ish, it was kind of a hodgepodge of proprietary solutions, both at the controller level and at the monitor level, such that interchangeability and interoperability between devices on the street was really difficult. You could get this to work with some equipment, but if you had to swap out to a different brand or a different model, you may not have a way to make it all come together. So that's the benefit of standards, is we hopefully arrive at some level of interchangeability and interoperability that makes the agency job of maintaining and deploying this much easier. So let's talk about the NEMA TS-2 amendment. I'll note that NEMA is about to publish the 2016 version of TS2, so this section on flashing yellow arrow will no longer be an amendment. It will be part of the NEMA standard. So until that happens, we can just consider it an amendment to the current level of the standard. So in that standard, in typical NEMA fashion, we have defined both the controller unit and the MMU operation. I'll mention right up front, we're referring to the MMU as an MMU2 device throughout this presentation. The significance of that is in the NEMA flashing yellow arrow amendment, there is a requirement that if an MMU is conformant to this flashing yellow arrow operation, it will be labeled an MMU2 instead of just an MMU. So that allows a user to look at their monitor to know whether it provides this functionality or not. Not all MMUs are required to support the flashing yellow arrow operation. So the standard started in 2009, directly following the MUTCD effort. It was completed towards the end of 2011, and it was published in November of 2012, as I stated, as an amendment to the 2012 NEMA TS-2 standard. It provides operation that is fully compliant to MUTCD 2009 definition, and there were some changes as a result of that MUTCD publication in the way that flashing yellow arrow was done prior to that. Right, so real quick, the controller section is not much change because we already had kind of the basics for that in overlap programming in most NEMA controllers. So we do have to define, though, that a flashing yellow arrow approach is a 4-section signal head. So now we have a red arrow, a solid yellow arrow, a flashing yellow arrow, and a solid green arrow. So now an output group for a phase will be 4 states. Again, it's based on the overlap concept when you're programming the controller for the permissive phases, permissive left turn phases. The red arrow is assigned to the overlap red, solid yellow to the overlap yellow. The flashing yellow arrow is assigned to the overlap green, and the green arrow is assigned to the protected movement. So both permissive flashing yellow arrow and protected green arrow operation Both use the same solid yellow arrow for the clearance interval. We'll see the effect of that when we get into the MMU operation. Now at this point, NTCIP object definitions for programming a controller for flashing yellow arrow operation are not yet defined, but that's going to be something that will appear likely in the controller ASC object definitions at a future date. So keep that in mind as well as you deploy this. The MMU is a little different. In an MMU, we're more hardware centric. We're dealing with load switches that have 3 outputs, MMU channel inputs that have 3 inputs. Everything has historically been done as a 3-input group, red, yellow, and green. Now we have a 4-section movement to monitor. So we're going to see that creates some interesting challenges with the hardware. So to keep the discussion clear, we have a number of terms we have to define. We're going to introduce the notion of paired channels here on the next slide, but we have a permissive turn channel. That's the flashing yellow arrow. A vehicle can turn left if there's a safe gap. We have the protected turn channel, which is the solid green arrow. That's fully protected. We have an opposing through channel. The opposing through channel is in the direction opposite of the left turn bay. This is where the motorist is looking to see a clear gap or a safe gap to turn. And we have this notion of paired channels, which I'll introduce in a minute. So one detail to mention here, the NEMA standard does not define a method of programming the MMU. So different brands or different models of MMUs, like in our controller, may have different methods, different menus, different procedures or parameters for programming the MMU. And as it says, interchangeability will be achieved once the MMU2 units are configured. Then you should be able to remove one MMU and replace it with a different MMU as long as they're programmed for the same mode of operation. This is not unlike our controllers of present day. So here's our notion of paired channels. We need to take hardware that's designed for 3 inputs and find a way to bring 4 inputs for the MMU to monitor. So to do that, we came up with the concept of a paired channel. So technically, each flashing yellow arrow approach requires 2 load switches and 2 MMU channels to monitor it. So in the simplest case, what I've shown here is load switch A provides us with the protected green arrow on the green output, and load switch B, what we call the permissive channel, has the red arrow, the solid yellow arrow, and the flashing yellow arrow. So that's considered the permissive left turn channel. Now, we have a challenge on load switch A because we have 2 outputs, the solid yellow and the solid red, that are likely not going to be used. So we have to deal with that. We'll discuss that later. There are cases where we may want to use those red arrow and yellow arrow outputs, but that's kind of a special case. I'll discuss that later. So the NEMA standard was written with a certain thought in mind. We came up with the idea for these channel modes, paired channel modes. The NEMA standard requires an MMU to support at least 8 of these modes. These are what I like to call pre-configured modes. Rather than have an infinite level of programming, we have pre-selected certain configurations and labeled them with a name A, B, C, D, etc. So while an MMU may have more programming than what's required in the standard, it has to at least arrive at the same final result. So the way that we would normally expect a user to select a mode is kind of based on what cabinet resources are available, meaning how many spare load switches do we have, how many spare monitor channels do we have to add flashing yellow arrow to a already configured cabinet, or maybe it's a new installation. Now, I'm going to show you how we go about selecting these modes, but I'll start off by saying the first 4 modes are basically straightforward, 2 load switches and 2 MMU channels per approach. We have a number of cases where we may not have enough load switches available. Part of what this webinar is going to assume is we have a 16-position back panel. We're in TS2 mode. We're not really going to discuss NEMA TS-1 12-channel mode, although it is supported by some of these modes. If we don't have enough load switches and or channels, we have to start getting clever. We have to start doing remapping. So we're going to reuse Ped yellow outputs. We have a number of different modes that can accommodate that. And then we have what the NEMA standard calls alternate modes that allow us to provide an 8-phase quad intersection with 4 flashing yellow arrow approaches, 4 PEDs, and still have 4 channels left over for additional overlaps if need be. Now, I'm going to describe how to choose a mode, but before we get into the discussion of the details of these modes, I'll point out that my experience so far has been most agencies do not need to use or even be experienced with all 8 modes. Most agencies that I've seen that have deployed this and have some experience will pick at most 2 modes. There are reasons for many of these various modes. A lot of the reasons come down to if it's a retrofit, it may save some cabinet rewiring, different considerations. If it's a new installation, then we don't have some of the same requirements that we do on a retrofit. So that opens up the choices here. But I think we've all learned the lesson over the years with experience that keeping things simple, keeping things straightforward, and perhaps most importantly within a jurisdiction, keep it consistent. So if a technician, every time they go to open the cabinet door to do some troubleshooting, find a plethora of different modes, it's going to be very confusing. So again, my experience has been pick 2 and try and standardize on those within your agency. So the first 4 modes, before we get into the detail, I'll give you the overview. The first 4 modes are what I call the simple configuration. There's no I/O mapping required in the controller. What you see on the back panel with the load switches is what you'll see on the MMU. If we have enough spare MMU channels, but we do not have enough load switches to add flashing yellow arrow, then we have to start making some trade-offs. This would bring us into modes E through F. For example, we may have only a 12-position back panel. Now we're adding 4 more load switches, 4 more channels. Well, we don't have the load switches. So we'll see when we get into modes E through F, we can remap the controller to reutilize Ped yellow outputs and kind of spread those out onto our spare channels. So as we go to these second level solutions, we'll find that the hoops we have to jump through get a little more complicated. For example, if we're going to retask Ped yellow outputs to drive flashing yellow arrows or protected greens, we no longer have the capability to monitor pedestrian yellow clearance intervals for conflicts during Ped clearance. So some of these may be worthwhile trade-offs, but they need to be considered in the decision point. The worst case is the cabinet does not have enough channels or enough load switches to add the paired channel combinations. that's when we go to mode G and H. So again, mode G and H, as you can see, the list of challenges grows, but if that's what we need to get the job done, with mode G and H, we can provide 4 through phases, 4 PEDs, 4 overlaps, plus 4 flashing yellow arrows. So in essence, it almost gives us a 20-channel MMU with 16 channels of hardware. So we'll talk a little bit more about that mode because it's a special set of conditions. It does require controller I/O mapping, so that's going to depend on the capabilities of your controller. Anytime we do controller I/O mapping, that creates complexity for technicians to maintain and replace the controller. There's another restriction here that the permissive programming for the flashing yellow arrow channel has to be the same as the parent PED phase programming. Ordinarily, this is the case, but depending on the geometry of the intersection, we may find it's not the case. In that scenario, modes G or H will not work. All right, so let's take a look at the details. That's kind of the overview. Here's an example of modes A and B. Mode B is probably the most common mode I've seen deployed. The difference between the two is basically which upper channels we assign the PED phases and which upper channels we assign the overlaps to. So this is just a convention. There is no right or wrong. I believe today the default convention for a NEMA TS-2 16-channel assignment is similar to mode B. The channels 9 through 12 are usually assigned to the pedestrian channels, and 13 through 16 are overlaps. If your agency is the opposite, then mode A would be the way to go. So in this case, we have on 1, 3, 5, and 7 the protected green arrows. In mode B, we have on 13 through 16 what we call the permissive channels: red arrow, yellow arrow, and flashing yellow arrow. So once we have this set up and configured, the signal sequence is, as you might expect, will go from red arrow if it's a protected left turn. Let's say on phase 1, we'd go from channel 13 is red, channel 1 would go to green. Once channel 1 is in green arrow, you'll note that channel 13 will be completely dark. No red, no yellow, no flashing yellow. So the monitor knows, based on our configuration and our choice of mode B, that as long as channel 1 is in the green arrow, it's okay for channel 13, the paired channel, to be dark. Once the protected green clears, channel 1 will go dark again, and channel 13 solid yellow will turn on for our interval, our clearance interval, and then we'll go back to channel 13 red. The permissive movement is simpler. We'll go from 13 red to 13, in this case it's the green input of the monitor, but it'll be the flashing yellow arrow signal to the motorist. To clear that permissive turn, we'll go to the same solid yellow arrow on channel 13 and then back to 13 red. So the sequence is actually quite logical and quite simple. It does take some getting used to as you're watching cabinet cycle, watching the MMU or watching the load switch indicators to get used to this. So the paired channel assignments are, in these modes, are already pre-selected. So channel 1 is paired with channel 13, channel 3 is paired with channel 14, channel 5 paired with channel 15, and channel 7 is paired with channel 16. All right, so that can't be changed. Again, if your agency prefers PEDs on 13 through 16 and overlaps on 9 through 12, then mode A would be a simple a simple choice. So again, my experience is most agencies are going with mode B as their standard configuration, and when they have cabinets that have other challenges, 12 position back panels, 14 position back panels, flash transfer relays in the wrong places, things like that, we'll see mode G or mode H provides another option to go to. So we're not going to go through every mode. I think you'll get the idea. Modes C and D are similar to A and B in that there's no I/O mapping. Everything is straightforward. The only difference here is we've swapped the position of the permissive channel and the protected channels. So the pairing is still the same in mode D, 1 and 13, 3 and 14, etc. This isn't necessarily any different or better than mode A and B. This might be a choice if you're doing a retrofit. Perhaps we don't have to pull as many new wires, or there may be some physical condition in the cabinet that makes this a better choice. But operationally, it's the same operation. All right, so A and B, C and D, B being the most popular or the most common mode to use. Now, we mentioned the possibility, well, maybe we have a 12 position back panel, maybe we have some other overlaps we need to use. We have modes E and F. In this case, the monitor is going to assume that we're going to remap the function of the Ped yellow output. Let me just start off by saying in most cabinets, that Ped yellow output, well, it certainly doesn't drive a signal visible to the motorist, but if you have a load in the cabinet, which most TS2 cabinets have, the monitor is actually watching that Ped yellow. It's on during the flashing don't walk interval, and that's how the MMU determines whether or not we might have a conflict condition during Ped clearance. So if we have to use modes E or F, we're going to give up that monitoring function to make this happen. So if we take a look at mode F, what we would do is we would I/O map the controller such that when it wants to go to the protected green arrow, it will turn on load switch number 9 yellow. The monitor will see load switch number 9 yellow turn on, and we are going to display and monitor it as channel 13 green. So there's basically I/O mapping in the controller to drive the load switch inputs, and there's I/O mapping, if you will, built into the monitor to break that protected green signal onto a separate channel. We have to do this because we rely on the soldered jumpers of the program card to determine the permissive matrix. So the way we're going to configure the monitor in mode F is we're going to program channel 13 for the phase 1, what's normally phase 1 protected green when we set up the jumper card, program jumper card. All right? So as this cabinet cycles, the controller will be driving the Ped yellows of the pedestrian load switches. The monitor is going to be monitoring them as channel 13 through 16 green. And again, our permissive turns are assigned to 1, 3, 5, channels 1, 3, 5, and 7. So a little trickier to watch. We have some I/O mapping. If your controller doesn't support I/O mapping, you have a problem. Most modern controllers do. So this is fairly simple to set up and configure. Again, the difference between E and F is just on the upper 8 channels, whether we put overlaps or PEDs on the high nibble or the low nibble. All right, as you can see, we're going to get into some other modes here. I'm not going to go through all of these, but I think the pattern is easy to spot. Modes I and J also use Ped-Y mapping. In this case, we're driving the permissive flashing yellow arrow signal with the Ped-Y instead of the protected green, okay? So again, one might choose this if they have a retrofit, and this provides an easier fit than perhaps rewiring the field. So let's talk about G and H. G and H are valuable if we meet all the requirements. Again, we've found with only 16 channels available in a NEMA TS-2 cabinet with a typical 8-phase quad with 4 PEDs and 4 flashing yellow arrow overlaps, that consumes all 16 of our channels. If that cabinet or that intersection also has some right turn overlaps or some additional overlap phases or other through phases, we're now out of channels. We have a real problem. So mode G and mode H are what NEMA calls the alternate channels. MMUs are required to support this mode, but it has some very different characteristics. Again, what it's going to allow us to do is combine the Ped-Y output like we did in the previous set in E and F, but rather than have the MMU remap it to a separate channel, we are going to leave the permissive flashing yellow arrow signal and monitor it on the same channel as the associated PED phase. All right, so here's how it looks. Let's talk about mode H. We have the protected turn channels as 1, 3, 5, and 7, and our permissive turn channels are going to be 13 through 16, which are also the same as our PED channels. So a couple things to note here. Number one, the permissive programming, the conflict matrix for the permissive left turn phase is going to use the same jumper settings as the associated PED phase. So channel 13, we're going to program the jumpers on the program card based on the permissive programming for phase 2 PED, phase 4 PED, phase 6 PED, and phase 8 PED. In general, the permissive programming for the flashing yellow arrow will be exactly the same as those associated PED channels. But this is something you have to confirm. There are some scenarios where they're not the same. If that's the case, mode G and H won't work. There's a couple other restrictions. One is if your cabinet or your intersection starts up in all yellow, this is not going to be compatible. Or if you're doing time of day flash where yellows are flashing, this will not be compatible. If you're flashing all red, not a problem. So again, there are some conditions where we can't take advantage of mode G and H. We just have to be sure before we get started that we've met all the requirements. So the other kind of drawback to this mode is, as you can see, the level of technician confusion is increased a little bit as we watch the intersection cycle or we troubleshooting a malfunction. Because the permissive turn movement is monitored on the same channel as the pedestrian movement, if we have a conflict involving channel 13, for example, we have to figure out, was the conflict because of the permissive flashing yellow arrow, or was it because of the walk indication for that associated channel? So it's nothing that can't be determined from figuring out who's turned on and who's turned off and what channels the conflict is involved in, but it does add another level of thought to the process. So modes G and H can be very handy. Again, we kind of have the capability to monitor as though we had a 20-channel monitor, but we only have 16 channels of hardware and load switches, but it allows us to have that 8-phase quad, 4 PEDs, 4 flashing yellow arrows, and up to 4 additional monitored channels. They don't have to be overlaps. They could be additional through phases, whatever you need to use them for. So that's basically how we determine which MMU mode we're going to pick. As I stated earlier, it depends very much on how many channels we're going to need, how many flashing yellow arrow approaches we're going to add, how many load switches we have, all of the hardware resources necessary to arrive at the final configuration. It's very important, if you're setting up a new cabinet, we need to consider the monitor programming first to get these channel assignments, and then we can program the controller, because now we already know the phase to channel assignments that the MMU is requiring. The MMU in this case is kind of more restrictive than the programming we have in most modern controllers. All right, I'm going to skip modes K and L. Again, these are additional variations of the modes we've already talked about. Needless to say, the MMU2-16LE provides 12 different modes. NEMA requires only 8. Somewhere in those modes, you're going to find one that will fit for your application. So that's basically the overview of picking the mode. Now our challenge is, first, what other monitoring functions do we get with flashing yellow arrow? And then I'm going to step through a quick example of how do we actually configure the EDI Smart Monitor to implement flashing yellow arrow. So there's a couple of things we need to be aware of. First off, to meet the MUTCD requirement of using the same solid yellow arrow to clear both the permissive turn and the protected turn, this added a new twist to MMUs, because the permissive programming for that solid yellow arrow will be different based on which movement we're clearing. So for example, if we're clearing the protected green arrow, when we go to the solid yellow arrow, it needs to be programmed conflicting with the opposing through phase. Yet when we're clearing the permissive flashing yellow arrow, that same solid yellow arrow is permissive with the opposing through phase. So effectively, the MMU needs to insert or remove the soldered jumper for that solid yellow arrow channel based on the sequence of the signals. So we obviously can't do that in the hardware. The MMU software will provide that different permissive programming. So we call that dynamic clearance conflict detection. Now this is something that happens automatically in the MMU. I don't think a technician normally will see the effect of this, but with one possible exception. If we are clearing the protected turn and we're in solid yellow and we have a conflict because of a hardware malfunction or even a controller malfunction, we have the possibility of detecting a conflict between two channels that are normally permissive. So we will see a fault shown on the monitor. When you look at the program card, the first observation will be, wow, I have a jumper installed. Those are supposed to be permissive. So again, it's a potential confusion factor. Make sure that you recognize that depending on the sequence, when the conflict involves the flashing yellow arrow, solid yellow signal, it may or may not reflect what the jumpers are on the program card. All right, we also have the option of monitoring for a stuck yellow or stuck flashing yellow output. If we're in the permissive turn phase and the flashing yellow signal is flashing, 500 milliseconds on, 500 milliseconds off. If it were to be stuck on for some reason, the load switch shorts on, the controller freezes up, some kind of cabinet malfunction, we have the option to detect that condition. Now, I'll mention it is an option because If we have this condition, we detect it as a fault, the MMU will put the intersection into flash. So it depends on whether that's the result we want to have happen, therefore it's programmable as an option. I mentioned earlier that on our protected green load switch channel, we have red and yellow outputs that typically will not have signal heads connected to them. So we know that in a NEMA cabinet, if there's no load on a load switch output, the monitor will sense that input as being active all the time. So historically, we would have to add a dummy load resistor or some kind of load to the cabinet wiring. We'd rather not have to do that. So if we're not using those red and yellow outputs, we can program the MMU to ignore them and force them to the off state. Okay? So those are kind of some new tricks that we need to be aware of in programming MMUs for flashing yellow arrow operation. So let's see how we do that. I've got some simple example here of the EDI MMU2-16LE monitor. We're going to show you the screen, the front panel screenshots. We can program this up right from the front of the monitor. We could use the EDI ECCOM software, set it up there, upload that configuration to the monitor. Several different ways to accomplish this. I'll just show you the front panel method. So our first step is to select the mode. So in this case, for this example, I've selected mode B. You can see that it's telling you up on the LCD display, we're in mode B. The permissive turn channels are selected as channels 13 through 16. The protected green channels are 1, 3, 5, and 7, just as we saw on the colored chart earlier. So on the channel icon displays, it's kind of reflecting the same thing. This is a good place to note if we're in type 12 operation, this happens to be a cabinet wired for TS1 operation, then the modes that use channels 13 through 16 will not be available. We have at our disposal modes A, C, G, and K. So the next thing we need to tell the MMU is of the 4 possible channel pairings, which ones are we actually deploying flashing yellow arrow on. In the maximum case, we'd have it on all 4 approaches. In this case, in this example, I've suggested we're only going to turn it on for 2 approaches on Main Street. So we've selected channel pairs 1 and 13 to be on and 5 and 15 to be on. So you can see once we've made that enable selection, the other icons turn off. So now we've told the monitor what configuration mode to be in and which channel pairs from 1 to 4 to enable for flashing yellow arrow operation. The third step is to select whether we are using the red and yellow outputs of the protected green load switch. Again, normally we would not. The default is those inputs will be disabled, or as the MMU describes here, in the off state. When it's in the off state, any voltage seen on the red and yellow input to the MMU will be ignored. This eliminates the need to have to hang dummy load resistors on those field outputs in the cabinet. There are some cases where you might want to use those red and yellow outputs. Typically the controller will drive the protected load switch as if it were a fully protected signal. So it will cycle the red, the yellow, and the green, even though we don't have signal heads on the red and the yellow. This can be handy. I've seen cases where, again, we don't have enough channels. We want to do a hardwired right turn overlap using the red, the yellow, and the green of the associated protected left turn. The short story is, if you have signal heads connected to those red and yellow outputs, we must enable these inputs to the monitor so that they will be monitored. So in that case, and in this example, I've assumed we do have signal heads on the channel 1 red and yellow, so I've turned on those inputs. Right? In most cases though, they'll all remain off. So the last page of the setup is to program 2 available options. The first is the flash rate fault. This is what we discussed earlier. If the flashing yellow arrow stops flashing, the MMU will detect that as a fault, transfer the cabinet to flash operation. If that option is in the off state, then we don't detect it as a fault, and we'll have to rely on maintenance or a motorist report to indicate there's a problem there. The second option is called flashing yellow arrow trap detection. We have the option to set a fault if the MMU determines that we've created a yellow trap. Now, I mentioned in the beginning of the presentation, because the permissive turn channels are operated as overlaps of the opposing through phases, the conventional yellow trap condition is eliminated in normal operation. However, whenever we do emergency preemption sequences, we have the possibility of going back and creating the yellow trap. So if a cabinet has flashing yellow arrow and it has preemption, I strongly encourage you, be sure that when you go into your preemption sequence, you're no doubt going to be clearing channels that may be in flashing yellow arrow. Be careful that you don't, again, create the yellow trap condition. So turning on this FYA trap detect option, if that's the case, the monitor will detect the yellow trap, set a fault mode, put the intersection to flash. In this case, the monitor determines the yellow trap is when the permissive phase has cleared to the solid yellow, but the opposing through phase is still in green ball. That's what the monitor considers to be yellow trap. That'll result in a conflict and a flash state. So looking forward, again, I mentioned this MMU2 naming convention. EDI no longer makes the MMU2-16LE. We have moved that product to the MMU2-16LE. It is identically the same product. It is, however, new firmware that provides the flashing yellow arrow support that we've discussed. So it is fully compliant with the NEMA standard. It is fully compliant with the MUTCD 2009 operation. If you have been using MMU2-16LE products, those came with 2 modes, basic FYA and what we called FYA compact mode. Those 2 modes are basically the same as mode B and mode F. So it's an easy conversion to make. The EDI MMU2 monitor I've already mentioned, besides the 8 required modes, we provide an additional 4 modes if one of them proves to be handy. So some frequently asked questions. Again, we can take any MMU2-16LE and by updating the firmware in it, convert it to an MMU2-16LE. How that's done, there are some details that need to be resolved, but it is simply a reflash operation. Depending on the vintage of the MMU2-16LE that you may have in your inventory, you may be able to update it yourself using our ECOM software. If it's older than 2009, then it has to come back to the EDI factory to be reflashed. But technically, all MMU2-16LEs can be converted to an MMU2-16LE and provide the NEMA flashing yellow arrow. So our policy is whenever a unit comes into the EDI factory for repair, we automatically update the firmware and it will be returned to you as an MMU2 MMU2-16LE operational level. So to wrap up, flashing yellow arrow is new technology. It has some very keen opportunities for moving traffic more effectively, providing operation that we weren't able to do before, increasing motorist safety. Federal Highway, when they first did the NCHRP study, found that there were 12 different methods of protected permissive left turns deployed across North America. Flashing yellow arrow, the 4-section scheme of MUTCD 2009, is intended to eliminate many of those variations and try and get some consistency. So flashing yellow arrow is new. There's a slight learning curve, but I think once you do the first deployment, the first intersection, it becomes fairly straightforward. So we're happy to introduce this new functionality to the EDI Smart Monitor. You'll find other tools that we don't have time to review in this webinar. The built-in setup wizard will help us configure those channels. So the operation will be to deploy an MMU, configure the program card as we would normally do, configure the flashing yellow arrow setup as I showed you in the previous slides. Then we would run the built-in setup wizard, and we now have an MMU2-16LE that should be ready to deploy in that, test and deploy in that cabinet. So we've kept this webinar moving. If there are any questions, we'll open up the webinar to submit your questions and try and provide some answers. This slide presentation will be available or is available in the support section of our website. Feel free to go look at that, read it again, look at the pictures. I'll mention for any 332 cabinet users, we have a similar functionality in our 2010-2018 series, but it is different. There's also an application note on our website that describes how that operation works. We'll also be doing a follow-up webinar for 332 users to understand how to program flashing yellow arrow into that style cabinet. So thank you for your attention and your interest in our products. Any email questions, questions that come up later, send them to editraffic.com, or I'm sorry, support@editraffic.com, and we'll try and get you answers to the best of our ability. So thank you very much.